This is how mail works. It says weight not over 1 ounce, then the price is 53 cents. Weight not over 2 ounces, price is 73 cents. And weight not over 3 ounces, the price is 93 cents. And then they have this wacky one, weight not over 3.5, the price is 1.13. And then we don't know what happens after that. We're mathematicians who work for this company. You have been given the job of figuring out how much it will cost, of making a formula so that when they plug in the weight, they can know how much it will cost immediately. Can we come up with a formula for this?
It's natural to consider a linear function, and so let's try that first and see what happens.
A reasonable first attempt would be to say, I'm going to make this y equals 0.2x plus 0.53. Let's say that instead of this y equals 0.2x plus 0.5, it's going to be y equals 0.2x plus 0.33. And that's an improvement because at least it gives the correct answer when I plug in 1. So let's do some reality testing here. Let's see if we say that this is our postage function. Does this actually match the values that we have? And in this case, getting the answer exactly right is important because we're spending money based on our prediction. And it's possible to create a formula that doesn't have any error.
So here we're going to do what I call a reality test. To what extent does the formula that we've proposed actually capture the behavior of the function? Piece of mail, this is a formula that we're proposing, and now we have to test it. So our proposed formula is linear, and if when x is equal to 1, y will be equal to 0.2 times 1 plus 0.33. So when x is equal to 1, y is equal to 0.53. And then I do that for the other values as well. And if I calculate, so far, so good, does match at these particular points. When we do x equals 3.5, what does our proposed formula give us here? The y value would be 0.2 times 3.5 plus 0.33, which will be equal to 1.03. The formula that we've proposed doesn't match the actual function behavior. So what would happen if we had a number between 3 and 3.5? So when x is equal to 3.25, if we look at this carefully, the actual function would have f of 3.25 is equal to 1.13, because it says if the weight is not over this amount, this is the price. Our formula doesn't capture that. We would have x equals 0.325, y equals 0.2 times 0.325 plus 0.33. I don't even have to know what this calculation is. I just know that this is not equal to 1.13. Our prediction here is not the same as what the actual function value should have been. So the first thing we're going to do is look to see if the function could be linear. And we're going to see if the slope between any pair of points is the same.
Said that we could plot points. So let's create a table here. Will that do it? Yes. Okay, that's way too big though. What do you think? 50? Looking at this function, and does it look linear to you based on what you're seeing here? These have different slopes at different places. Linear functions always have the same slope no matter where you look, right? But if you look here, you can visually see it's very clear that these have different slopes.
Well, we can calculate the slope from x equals 2 to x equals 3. And the slope of this function will be f of 3 minus f of 2 over 3 minus 2. My f of 3 is 0.93, and my f of 2 is 0.73 over 3 minus 2. This slope from x equals 2 to x equals 3 would be equal to 0.2. Now I'm going to compare that to the slope from x equals 3 to x equals 3.5. So from 3 to 3.5, I look at f of 3.5 minus f of 3 over 3.5 minus 3, change in f, change in x. I have 1.13 minus 0.93 over 3.5 minus 3. And I can see that that's going to be 0.2 over 0.5, which is 0.4. So these two slopes are not the same. They're not even close to being the same. So we cannot represent our function by a linear function because the slope or the average rate of change isn't even close to being constant between different points. Also, we have no reason to think that it's linear. We have no reason to think that the price would smoothly increase as the ounces increase. The idea to try some different types of functions. So using a calculator, we've come up with a quadratic function and an exponential function that fit these points well, and we see if they could actually work to describe the price that we're looking at. Let's look at this quadratic model first. Why doesn't this quadratic model work? So this actually this will make a prediction for 5 ounces, and we can't have that. If you can't give an answer based on the information you have, it is better to just say, I don't know the answer. This is making a prediction that f of 5 would be 1.69, but in fact, we don't know what f of 5 would be. Our data didn't give us any information to predict f of 5. This needs a domain restriction. We're only going to be able to make predictions for things that are between 0 and 3.5 ounces to be sure that we enforce that. You can do that in Desmos pretty easily by doing this left curly brace, which is shift above the square bracket, but I need to be sure that this formula is only valid up to 3.5. Notice now f of 5 is showing as up as undefined, and that's a good thing. F of is another issue. This doesn't even make the right prediction for x equals 3, does it? The prediction that this makes is f of 3. If you look at f of 0.93, and it's actually 0.96. And that 3 cents error in business is something I'm not going to want to do. We tried 2 linear functions. Now we've tried a quadratic, and it didn't work. Let's try the exponential. I think the exponential is going to have similar issues. This is predicting that if I mail something weighing 0 ounces, it costs me about 50 cents. So a reality test here is, what would I expect to happen if I mail 0 ounces? Should be $0. This model violates that reality test. I'm going to throw it out on that basis. So both of these were good ideas worth considering, and both of them are going to end up not being what we use. Pause. We need to think about the fact, function be smooth or should it have abrupt jumps? The price function. It's not the case that it should be abrupt because it's arbitrary. It's not the case that they could change the price tomorrow. If they change the price tomorrow, we need a new function. It should have abrupt jumps because if I go from at 1.0 ounces, what should the price be? 0.53. At 1.000000001 ounces, what should the price be? 0.73. If you trigger over 1 ounce, they're raising the price on it. You have to remember, this is a robotic automated thing. They don't have a human being weighing it and saying, oh, they're close. It's over 1 ounce. I don't care how much it's over 1 ounce. It's going to be more. So our graph should have a behavior where it's like at 1.0, this should be equal to 0.53. And as soon as I get above 1.0 at all, it should jump to 0.73. Now, what happens if I'm just slightly below 1.0? I'm thinking my graph should look like this. Yes, this is a piecewise function. This is a rough sketch of our graph that could work. You see, this graph captures the fact that for anything less than 1 ounce, price should be 0.53. And for anything, there's this abrupt jump where as soon as you get even a little bit past 1 ounce, price jumps up to 0.73. These abrupt jumps are characteristic of piecewise constant functions. They're called piecewise constant because their pieces are constant. Their graphs look like stair step. We can come up with a formula, and I realize this formula doesn't look beautiful like f of x equals x squared, but it does the job perfectly well. And so we've done it. This is a formula that captures the information we were looking for. We're only concerned with predicting what happens between 0 to 3.5 ounces. We don't have to worry about predicting anything outside of that or trying to extrapolate from the information we have.